Hello there and welcome back to this video series on control systems. Over the past few videos, we have been seeing time response analysis, and we see that response and stability are two important aspects when we design any control system. After watching this video, you'll perhaps be able to specify what is a bounded signal, what is BIBO stability, bounded input, bounded output stability, and find if a system with given closed loop poles is BIBO stable or not. In general terms, we want to have the system behave well when it is subjected to inputs and disturbances. This well-behavedness we express in terms of stability. We say that a system is stable if the system comes back to the initial condition when there is a small disturbance. On the other hand, we say a system is unstable if its output diverges when a small disturbance occurs. When a system is marginally stable, it is on the borderline of stability and instability. The output oscillates continuously when there is a small disturbance. To make it a bit more clearer, we say that if small inputs lead only to small outputs, the system is stable. And this leads us to the definition of bounded input, bounded output, BIBO, BIBO stability. And for defining BIBO stability, we need to know what we mean when we say a signal is bounded. Okay, a signal is bounded if there exists a delta such that magnitude of C of t is less than or equal to delta for all time to come. For every possible value of t, the C of t is less than or equal to a single value delta. If this is true, then delta is greater than every Ct for all time to come. This is an example of a bounded signal. Okay, if you draw a line here somewhere at the top of this, then every point on the curve is less than the bound we have drawn here. So that is, there is an upper bound here below which only the curve lies. That is why it is bounded signal. Similarly, if you see this signal in this plot, there are two graphs shown here. One is R of t, second is C of t. This R is going horizontally forever. This C is gradually approaching R of t. In either case, if you draw a line here, horizontal line at 1.2, every value of RT is less than 1.2. Every value of C of t is less than 1.2. That is, there is a bound at 1.2. You can say 1.2 or 1.1 or whichever value greater than R and C. So this is a bounded signal RT and CT. Then if you see the sinusoid, every value of this sinusoid is less than 5. The magnitude of every value is less than 5. So this is also a bounded signal. And this we say are sustained oscillations. Okay, the value here is oscillating between +5 and -5 according to a formula. So this is still bounded but oscillatory. This is definitely unbounded signal. You can see it is growing boundlessly. You can see here as t tends to infinity, C of t tends to infinity. So it is a bounded signal. With this notion, we say that a system is bounded input, bounded output stable if the response of the system to every bounded input is also bounded. Every is a keyword here. Even if there are 1000 inputs which give bounded output, that is not sufficient. If there exists any one input for which the response of the system is unbounded, we say the system is unstable. And we say that a system is BIBO unstable even if the response to any one bounded input is unbounded. If this happens even for one input, the system is not BIBO stable. It is BIBO unstable. We'll try to make it more rigorous by trying to look at the math behind. Consider a system GS with input RS and output CS. In time domain RT and CT. For that you can give the output and input relation as output is equal to transfer function multiplied by input. And if you take inverse transform, we will come to this convolution integral. CT can be given like this, where this G is impulse response. We want bounded input, bounded output stability. So we say that if RT is bounded, every value of R of t, magnitude of every value of R of t is less than M, which is a finite quantity. We use this information in the convolution integral and say that the C of t is less than or equal to M multiplied by this integral. That is, in place of RT we put M. If you put the maximum value, then this equal to has to be substituted with less than or equal to, and Ct is less than or equal to M integral so and so. Thus, if we want C of t also to be bounded, this integral better be bounded by a value n. So we say that a system is BIBO stable, bounded input, bounded output stable, if and only if its impulse response is bounded. So this if and only if works both ways. A system is BIBO stable if its impulse response is bounded. On the contrary, if the impulse response is bounded, the system is BIBO stable. This will further quantify. Let us say this is the transfer function of the system, and S is equal to 0 will give you the zeros of the transfer function. ds is equal to 0 will give us the poles of the transfer function, and this ds is equal to 0 for a closed loop system is called the characteristic equation of the closed loop system. If we assume that poles are distinct, then by partial fraction expansion you can write this. If P1, P2, P3 so on are poles, you can split this into partial fractions given here, and in general a kth term will be ak by s minus pk. If you take inverse transform of this, ak e to the power of pk t. So if you take inverse transform of g of s, you have terms such as a1 e to the power of p1t plus a2 e to the power of p2t and so on. And you can see that if each of this p, each value p1, p2, p and so on, if each of them is less than 0, each term decays down. Each time decays down, and we say that the impulse response is bounded. If each pole is less than 0, if the real part of each pole is less than 0, the system is stable. If any one is greater than 0, the system is unstable. And if it is 0, then also the system is stable. We can generalize this treatment and say if the real parts of all the poles are negative, then the system is BIBO stable. Just remember this line, commit to memory. If the real parts of all the poles are negative, then the system is BIBO stable. Even if the real part of one pole is positive, the system is unstable. That is, if 99 poles have real parts less than 0 and one pole has real part greater than 0, the system is unstable. Condition is that real parts of all the poles must be negative. We will try to generalize and repeat. If the real parts of all the poles are negative, system is BIBO stable. Even if one pole has positive real part, the system is BIBO unstable. If non-repeated poles lie on the imaginary axis, the system is marginally stable, that is, there are sustained oscillations. And if repeated roots lie on the imaginary axis, the system is BIBO unstable. We'll try to see what these non-repeated and repeated roots lying on the imaginary axis in the subsequent slides. So that's all we have. We can summarize this as given here. The stability of a system can be inferred from its poles. Then if all the poles are negative, the system is stable. If any one is positive real part, then the system is unstable. Repeated poles on the imaginary axis, system is unstable. If non-repeated poles lie on the imaginary axis, the system is stable. I think that's all we have for now. Have a great day.